Here we're going to find out the mutual inductance of two coplanar coil or two concentric loops here. So let's try to understand the situation first here. We have one large coil here, and the current is passing through this coil, and this is again an oscillating current, that is a changing current. Because the currents are passing through these coils, the magnetic field, it will produce the magnetic field. So now let's say at any point the direction of the current is this way. So if you hold this coil so that your fingers coil, right hand fingers coil in this direction or curl along this direction, then your thumb will point out in the direction of the magnetic field. So in this case, the magnetic field direction is going from the top of the coil and coming back again, going from the top of the coil and coming back again. So it's a circulating. The magnetic field always start from one point and comes back, so it's always a closed loop here. So that's the direction of the magnetic field. Again, if you have any confusion finding out the direction of the magnetic field, please watch my other videos here. And then we have a second coil that we can call as a pickup coil or a secondary coil here. So in this case, the radius of the coil, the 2, is much smaller than the coil 1. Then you might be thinking, why? What's the rationale for this one? The rationale for this one is, if this radius or if this area of the coil 2 is smaller, then almost we can consider that the uniform magnetic field passes through this one, or at any point inside this coil the magnetic field does not change. Okay, so we can in fact solve this problem with a homogeneous magnetic field. When I say homogeneous magnetic field here, that means the magnetic field at any point within the coil 2 is constant. Okay, so let's first find out what is the magnetic field due to this coil here, and that is given by B1 equals to, that is the magnetic field produced by the coil 1, is mu 0. What is mu 0? The mu 0 is the permeability of the free space. I1 is the current passing through this coil, and R1 is the radius of the first coil. Okay, and here I am mentioning one more time, the radius of coil 2 is much smaller than the coil 1, or the coil 1 is much bigger than the coil 2. So the flux passing through this coil here, the second coil here, the flux passing through this coil can be given by the magnetic field times the area of this coil here. Okay, so here that's the magnetic field times the area of this coil here. So this magnetic field is at the center of the first coil, and if we assume that the radius of the coil 2 is much smaller compared to the R1, then at any point within this coil, there will be not much changes in the magnetic field. That's the reason we assume the radius of the coil 2 is much smaller than the coil 1. Okay, so the phi 21, what does this mean? Is the flux through the coil 2 due to the coil 1. So how do we find out this flux? What is the magnetic field here, and times the area of this vector here. The magnetic field times the area vector. And also the other reason of assuming the small area or the radius of R2 is smaller than R1 is, so that the area vector and the magnetic field vector are in the same direction. The correct equation of this one is B vector times A vector. That's the dot product, and the dot product is given by BA cosine theta. So if we assume this coil 2 is much smaller, then the area vector and the magnetic field vector will be in the same direction, and that's the reason we assume the coil 2 is much smaller than coil 1. So we got get the value of B1, so you simply plug in here. What's the area of coil 2? Pi R2 square. So let's rearrange these terms. We get this term here. And what is the definition of the mutual inductance? The flux passing through this coil, divided by the current passing through the bigger coil here. So the flux divided by the current. Remember, this flux is through the second coil, and this is the current in the first coil. So if you do that, then we get this term here. And look at this equation here. This equation does not contain current, so that means the mutual inductance does not depend upon the current. It only depends upon the geometrical parameters. In this case, the geometrical parameters are the radius of the first coil and the radius of the second coil. Okay, so this is it from this video, and in the next video we're going to talk about the LR circuits where the current is growing and the current is decaying. I will see you in the next video. Thank you.